All right, it's now 3 minutes after, and we have our very own Chen Zhang speaking to us from Toronto. Is that correct?
Yeah.
Yeah, and you can see his slides. You can also, he was very kindly shared his slides in the chat. You can see them there. And with this, I yield the podium to Chen Zhang.
Mhm. Okay, yeah. Uh, uh, Thank you very much for the invitation. It is always a great pleasure to speak at this seminar. This is my first time to speak at this seminar. During my 5 years at Columbia University, I also learned a lot from this seminar. So today, I'm going to give a survey style talk. So so the talk today is going to be about the stable aminos for the covalent bond of the flag varieties and some of its applications. So this will be based on many joint works with my collaborators. Yeah, I put the references at the end of the slides. Okay, so let's begin. So let's begin with some notations. I can send it again. So the group G is a reductive group over the complex numbers. You can just think of this as a GLN. And we fix a Bell subgroup and a maximum torus. And then we form this quotient G mod B's. So throughout this node, I will use X to denote this quotient G mod B. So this is called the flag variety. So it consists of all the Bell subgroups. So, for example, if G is GLN, then the flag variety is just these sequences of the linear subspaces V1 contained in V2 contained in Vn, and each of Vi is just the dimension I. So one of the good properties of this flag variety is the following. So if you consider the covalent bundle of it, so then this will be a resolution of some singular variety. So and so the singular variety is just the nilpotent cone instead of the dual of the Lie algebra. And this map is just the moment map. So the group G acts on the covalent bundle, and and this is a symplectic variety, and then you can just take the moment map. So this is called the spring resolution, and this is the most classical example of this variety is called the symplectic resolutions. Anyway, so and my talk today is going to focus on this variety. although although the general theory exists for the general symplectic resolutions. So my talk will consist of two parts. So the first part, we will restrict to the cohomology case, and in the second part, we will talk about the equivalent K-theory case. So first of all, let us review the definition of the stable basis. Since this is a talk at Columbia University, I think most of the audience are already very familiar with these stable aminos. And in our case, for the spring resolution, it is even easier for me to introduce the definition. So anyway, so let's look at our varieties. And so we have two groups acting on this. So one is this maximum torus T. So T acts on the flag variety by left multiplication, and then it will induce an action on the cotangent bundle. Another action is the C stars. So because this is a cotangent bundle, so it has a natural torus action just by dilating the cotangent fibers. And so this is C star only acts on the cotangent fibers. It acts trivially on the zero section. So it acts trivially on the flag variety. So anyway, so this T will preserve the symplectic form, but this C star will scale the symplectic form. And I just use this H bar to denote this equivalent parameter for this actual C star action. Okay, so first of all, so if you consider the equivalent cohomology of a point, then this is just the functions on the Lie algebra of this torus. So i.e. functions on the Lie algebra of the maximum torus on the Cartan subalgebra, drawing this equivalent parameter H bar. Okay. So if you consider the torus fixed points on this Springer resolution, so then these are, so first of all, the torus fixed points will lie on the zero section, and if you consider the torus fixed points on this flag variety, so then this is in one-to-one correspondence with this well group. So W is the well group. so the correspondence goes as follows. So if you have an element here, so then you can conjugate the starting bra by this well group action. So then we get another bra, and the coordinate direction is just 0. So it's less in the 0 section. And now we use this notation. So if gamma is some cohomology class, so we use this gamma restrict to W. This means the pullback of this cohomology class to these fixed points. So this realizes in the equivalent cohomology of a point, i.e., this will be some polynomial on the Lie algebra of the torus drawing this formal variable h bar. So on the flag variety, so so if you have reductive group G, then you have the Broussard decomposition. So then we have a decomposition for the flag variety, which is just a discrete union over the Y group of the Schubert cells. So BWB, and then you divide it by B. And I will use, so throughout these nodes, I will just use XW circle to denote this Schubert cell. So this is isomorphic to a Fn space, and the dimension of that Fn space is just given by the length of the corresponding element in the Y group. Okay, so this is all well known. And then I just use this XW to denote the closure of this Schubert cell. And then this will be just the disjoint union of the Schubert cells over Y, and Y is another Y group. Y is runs over the elements in the Y group such that Y is smaller or equal than W. So this order is just the usual Broussard order. Anyway, so since this is a symplectic variety, and then there are many interested in Lagrangian subvarieties inside this Springer resolution. And so the typical ones are just the conormal bundles to the Schubert cells. Okay. So then by localization, so then this is easy to see. So if you just take a closure of these Lagrangian subvarieties, and so this will be a closed subvariety inside the Springer resolution, and then just consider its fundamental class of these closed subvarieties. So then these classes as W runs over the Y group elements. So then this will form a basis for the localized equivalent cohomology of the Springer resolution. But unfortunately, so although this class, the construction of these classes is very simple, but this is very hard to study these classes. Anyway, so because this is too singular. For example, I think even now we don't know the restriction formulas for this type of classes. Anyway, but a very smart idea of Andre and David Maulik is the following. So this is the theorem. So this theorem defines the stable basis, and this holds in a much more general setting. For example, the symplectic resolutions. And now let me just state this in the situation of the Springer resolution. Okay, so this basis is very hard to study, but you can modify this basis to get a well-behaved basis. So their theorem says, so we can find some integers, and then we form this linear combination of these conormal bundles. But here, but this transition matrix, we want this to be a triangular matrices. Okay, so this if you start with W, then we only sum over those Y which is smaller or equal than W under the Broussard order. So these coefficients, they are integers, and moreover, we can control the leading coefficients. So the leading coefficients, they are determined. It is either 1 or -1. Let me not write down the precise formula for this. Anyway, it can be fixed. Okay. So then what are the properties of these classes? So the defining properties is the following. So this is called the degree condition. So that so W corresponds to some fixed points, and then if we pick some smaller fixed point, we pick some element which is smaller than W, and then we can pull back this class, this cohomology class, to these smaller fixed points. So then this will relies in the equivalent cohomology for points. So i.e., this is just some some polynomial, and then you can consider the degree of this polynomial, but we only consider the degree with respect to this Cartan subalgebra. So we don't consider the degree with respect to the whole torus. We only consider this corresponding to this torus fixing the symplectic form, and the condition is as follows. So then this degree, which is some integer, has to be smaller than the degree of this stable class of y raised to y. And then by definition, this is just equals the dimension of x, because if you look at the this element and if it restricts to itself, so then the only contribution are the one coming from the leading term. So because all these lower classes, if you restrict to w, so then this will be 0, unless y equals to w. But since each of them is a Lagrangian subvariety, so then you will get then this degree will be just the degree of the dimension of x anyway. Okay, so and for the symplectic resolution, so then an easier way to characterize this condition is the following. So recall, so this is a polynomial on the Lie algebra of the maximum torus, and also a polynomial on the H bar. So then this so because all of these are Lagrangian subvarieties, so then if we require the degree with respect to t is smaller than the dimension of x, so then this just says this polynomial has to be a multiple of this h bar, so it should be divisible by h bar. Okay, so this is the definition in our case. Okay. Okay, so then so because of this triangular properties, so then all, if you put all these slab plus w together, so then this will form a basis for the localized cohomology, and this is called the stable basis, or maybe called the stable envelopes. And I forget to mention, so this plus, so this plus is the, so this is a dominant where. So the definition so their definition depends on the choice of a chamber, and in our case, a chamber is really exactly the same as the usual Weyl chambers. And here I'm using this plus to denote these dominant Weyl chambers. Okay, so let's look at a very simple example, i.e. when G equals SL2, so then the flag variety is just the P1, and the Weyl group just consists of 2 elements. And then, so the Schubert cell, so corresponding to identity is just the point corresponding to this 0 instead on this P1. And the other Schubert cell is just the P1 minus 0. So then by definition, so then the stable basis corresponding to the identity element. So this identity is just this one. So there's no element smaller than identity. So we only have this cotangent space at 0, and the sign is this can be fixed. And then for the other element S alpha, so then so the conormal bundle to this Schubert, the closure of the conormal bundle to this Schubert cell is just the P1, and so then this will be just the linear combination of P1 and the cotangent fiber at 0. And the theorem and the theorem, so this exists in uniqueness tells us that this coefficient has to be 1. So anyway, so these 2 coefficients, they have to be equal to each other. Either both of them are +1 or both of them are -1. So this can be seen as follows. So we take this class and then we restrict it to this 0 fixed point. So what is the contribution of P1? So if you have a P1 and then you restrict to 0, so then you will get the weight of this cotangent space, which is alpha minus h bar, and then this restrict to 0, you will also get this cotangent space, which is negative alpha. So you will get, so this restrict to 0, so you will get you will get a minus h bar, so which is divisible by h bar. And you can see this coefficient can only be 1. It cannot be arbitrary coefficients. Anyway, so this is the definition. So I think this should be okay. Okay, so any questions? Okay, so why is this basis very good? So there are some symmetries on the cohomology of the Springer solutions, i.e. the Hack algebra action, which is degenerate Hack algebra actions. So the definition of the degenerate Hack algebra is follows. So first of all, the generators of this Hack algebra is this TW as W runs over the elements in the well group, and some lattice part X lambda. Lambda is a character of the maximum torus. So this X star of T denotes the character lattice. And the relation is as follows. So this TW just satisfies the usual relation in the well group. So the square equals the identity, and also this braid relation. And this X lambdas. So this so the subalgebra generated by X lambdas is isomorphic to the equivalent cohomology of a point. And the commutation relation between these two is given by this relation anyway. So this is degenerate Hack algebra. So one of the classical result about this degenerate Hack algebra is the following. So we can recall this the cotanent band of the flag variety is the resolution of the Neapolitan cone, and then we can form the fiber product with itself. And then we can consider the Bramah homology of this. Okay, so this is called the Steinberg variety, and this is the Bramah homology. So then first of all, this will have an algebra structure by convolution, because of the you can consider 3 copies of the cotanent band of flag varieties, and then you can form the push-pull. Anyway. So the Lucas theorem tells us that then this convolution algebra is isomorphic to this degenerate Hack algebra. Okay, and again, if you use convolution, so then this convolution algebra will act on the T equals C star equivalent cohomology of the cotanent band of the flag variety. So if you have a class here, so then you can pull back to this fiber product, and then you push forward along the first component. So then this gives you an action. So so the good properties of the stable basis is the following. So if you take a simple reflection S alpha I, so then I think so if I use the so then this should be T S alpha I. So if you take a simple reflection and then corresponding to consider the corresponding element in this degenerate Hack algebra, so then it acts on the stable basis in a very simple way. So you just multiply on the right. Okay. So then this just says this classes that will be a standard basis for the action of this Hack algebra. Okay. And then so once we have this formula, then this will be very then it is very easy to deduce all the good properties about these classes. I.e., you can find out the localization formulas for these classes, and the localization formulas is again can be used to study the common cohomologies of this cotanent band of flag varieties. Okay. Anyway, so Anyway, so the good properties of this stable basis, they behave very well under this Hack algebra action. And then the other place we can see this Hack algebra action is the following. So here we see the Hack algebra action in the world of this cotanent bundle. But you can also see this Hack algebra action purely on the zero section on the flag varieties. Maybe, so I think. Okay, so this Schubert varieties. So the fundamental classes of these Schubert varieties will give you a basis for the cohomology of the flag variety. Right? And then so then this basis will behave very well under the BGG operators. So this push pull from this G mod B to G mod PI. PI is a minimal parabolic subgroup. Those BGG operators, they will also form a hack algebra, but the Dutch hack algebra is called the neo hack algebra, i.e. the square. So that so their squares will be equal to 0 instead of 1. So if you just consider the cohomology class of the Schubert varieties. Okay, but if you want to get this degenerate hack algebra action, then we should also degenerate. So then we should also deform these Schubert classes, and then this so this classes is called this Chen-Schwarz-McPherson classes. Okay, so what are these classes? So on the so we consider two functors on the set of varieties. So first the first the functor is just this homology functor. If you have some variety, you can take its homology. And the other functor is the constructor function functor. I.e., so if you have a variety, then you can consider all the constructor functions on that variety. So then we have two functors, and then so then this series just says there exists a natural transformation, and denoted by C star between these two functors, and satisfying some normalization conditions. So if we start with a smooth variety, so then this and then if we apply this natural transformation to this identity function on this smooth variety, so then we should then we just get the original chain class, the original total chain class of the tangent bundle of y, and then kept with the fundamental class of y to get into the homology of y. So anyway, so this is called the CSM classes. So this is just some chain class series satisfying some nice property, i.e. it commutes with the proper push forwards. And if the variety is smooth, we just get back to the usual chain class series. Okay, and now in the cohomology of the flag variety, we want to consider these classes. So recall on here on the flag variety we have the Schubert cells, and then we can just consider this identity function on the Schubert cells. So this will give you a constructor function on the flag variety, and then we apply this this chain class theory. So then we get some cohomology class, and then in the equivalent cohomology of the flag variety, and then we will denote this by the CSM of this Schubert cell. Okay. So in a work of my collaborators Aluffi and Mihalcea, so they also study this degenerate hack algebra action on the cohomology of the flag varieties, and they study this action on this CSM classes. So their formula is almost the same as before. So if you apply the simple generator in the degenerate hack algebra to these CSM classes, so then this will just move the CSM class of one Schubert cell to another Schubert cell, so which is really in the exact same shape as before. And then they made the following conjecture. So okay, so now let's just refer to the non-equivalent cohomology. So then this class we can write this as a linear combination of the classes of the Schubert varieties. So y is smaller equal than w, and the leading coefficient is also equals 1. So then anyway, so you can just regard this as a definition of the Schubert classes, and then so they conjecture so these classes, so these coefficients, they has to be non-negative. And also this conjecture, they also made this conjecture in the equivalent cohomology case, i.e. so then this will be some polynomial, and so then they conjecture this is to be a positive linear combination of this product of these positive roots. Anyway, So the Grassmannian case is proved by Junhe, and so his proof also works in the equivalent cohomology case. So later we proved that this conjecture holds for any G mod P, and P is a parabolic subgroup. So for any partial flag varieties, but only in the line we can only prove this in the line equivalent cohomology case. We cannot prove this in the equivalent cohomology case. So the idea is the following. So here the stable basis usually plays a very important role. So the first is as follows. So we consider this inclusion of this flag variety inside this container bundle, and then inside this container bundle leaves this stable basis, and then if we pull back this stable basis to the zero section, and then we let this h bar equal to 1, then we just get this CSM classes of the Schubert cells. Okay, so because this Dutch axis actually C star acts trivially on X, so then if we consider the Dutch C star equivalent cohomology of X, so then this is just the cohomology of X joined Dutch formal variable h bar. So that's why we can let h bar equals 1 here. So here you can just get this equality by comparing the degenerate Hacker algebra actions. And the other ingredient is the following. So these stable bases are just some linear combination of these conormal bundles. And in symplectic geometry, another way to see this Lagrangian subvarieties as follows. So if you have some D modules, and then you can consider its characteristic cycles, so then we can also get the linear combination of these conormal subspaces. So it says, so this stable basis is just the same as the characteristic cycle of some D module on the flag variety, and the volley is such a D module. So that D module is associated to some Warman module under this Bennings and Bunsen localization. So this rho is the half sum of the positive roots, and then this is the Warman module with this highest weight, and then we can pencil over the universal enveloping algebra of the Lie algebra with the shift of differential operators on the flag variety. So then we will get a holonomic D module on the flag variety, and then we take the characteristic cycle, and then we consider the classes formed by this characteristic cycle. So and then this will coincide with the stable basis. Okay? And then so the characteristic cycle of a D module is always a positive linear combination of the conormal bundles. So then we will have some positivity here, and then so then we can use this positivity to prove the positivity for this class. But there is also, but it's not a very simple way. There is still some work to do. So if you pull back some effective class to the zero section, you may not get some effective classes. Yeah. Anyway, but the key idea is just use the positivity of the characteristic cycle of the D module. Anyway, so yeah, this is all I want to say about this cohomology story. And then I will go to the equivalent K-series case. But so any questions before I go into the K-series case? Okay, so the part 2 is about the equivalent K-series case. So the notation is as follows. Yes.
So are there similar expectations or something in the equivariant case that just can't be proved, or is there no way to make sense of how this conjecture would look?
Yeah, that is a very good question. So there's another construction to go from this container bundle to the zero section, called the secret class construction. But the Dutch construction will not preserve the equivalent positivity. Yeah, so anyway, our argument will not work in the equivalent case, but I don't know whether there will be other clever ways. Yeah. Is that okay, Noah?
Yeah, thanks.
No problem. Thanks for the question. Okay, so and now let's go to the K-theory case. So so we use this to denote the T cross C star equivalent K-theory of the coordinate bundle of the flag variety. By definition, this is just the Grothendieck group of this T cross C star equivalent shifts on the coordinate bundle of the flag varieties. So this is a module over the equivalent case of a point. So the equivalent case of a point is just the functions on the torus, so functions on the T cross C star, and here and in the K-theory case, I will use Q to denote this K-theoretical equivalent parameters for this actual C star, i.e. Q will denote the standard representation of this C star. Okay. Okay, so then the theorem, the definition of the K-theoretical stable envelopes. Okay, so this is the work of Andre and his many collaborators. So in our case, this says the following. So again, so first of all, this will depend on the choice of some well chamber, and it has a additional parameter L. L is some T equivalent line bundles on the coordinate bundle of the flag varieties and the tensor with the rational numbers. So this has to be we need this tensor ring with rational numbers to. So we need to pick a generic L. I.e. we need to pick some good rational numbers anyway. Anyway, so the theorem says the following. So these classes will satisfy the similar properties as before. I.e. Previously we have this conormal spaces, and then we can consider the structure shape of the conormal bundles, and then this will also be a linear combination of the structure shape of the conormal bundles, and the transition matrix is again a triangular matrix. But the Dutch coefficients are realized in the localized equivalent cohomology of a point. So the most important condition, the degree condition, it becomes as follows. So again, so if you pick an element y, which is smaller than w, and then so this will be some equivalent K-theory class, and then if you pull back this to some other fixed point, so then first of all, this will lies in the equivalent K-theory of a point. So i.e. so then this will be some function Laurent polynomials on the maximum torus T cross C star. And if you have some Laurent polynomials, so then we can also define this notion of this degree of a Laurent polynomial. So, but again, we only consider the degree with respect to this maximum torus T, not this C star. So then this will be some polygon lying inside the character lattice of T tensor with the real numbers. Okay. And then, so the condition is as follows. So then we require this polygon is contained in the other polygon. But there is a shift, and here it comes in the this parameter L, and then so this shift is determined by these two difference of these two ways, L reduced to y minus L reduced to w. So in particular, so then this condition does not depend on the linearization of this line bundle L. Okay, yeah, I think this should be okay because I think most of you are familiar with these notations. Okay. So the first so as in the cohomology case, we have this hack algebra action, and in this case we will also study. First of all, we will also study the hack algebra action. And in the K-theoretical case, so then this will be the affine hack algebra instead of this degenerate hack algebra. So, okay, so quick definition. So what is this affine hack algebra? So, so the generators is the same as before. So W runs over the Y group elements, and this X lambda runs through this character lattice. So then this TW will satisfy this quadratic relation and also this braid relation. So previously, in the cohomology case, this Q equals 1. And these X numbers will generate the subalgebra isomorphic to the equivalent case of a point. And the commutation relation between these two is is given by this. Anyway. So again, there is some very classical result in geometrical representation theory. So previously we consider, so this is the Sternberg variety. So previously we considered the Bramah homology of this Sternberg variety, and it is isomorphic to the degenerate Hecke algebra. Yeah, so if you replace the Bramah homology by the equivalent K theory, so then again, by convolution, this will have the algebra structure. So this is a convolution algebra, and this algebra is isomorphic to this Alban-Hecke algebra due to the work of Castellan, Lustig, and Ginsburg. And then again using convolution, so this convolution algebra will act on the torus equivalent case of the cotangent bundle of the flag variety. Okay. And then yeah. So in the remaining of the talk, I think I will fix this line bundle L to be some rational number if U is bigger than 0, but it is very small, it's very near 0. So this number times this L rho. So if you have a torus weight, so then we can form this line bundle over the flag variety. Okay. And this L rho. Anyway. Okay, so the a very similar theorem as before is as follows. And now if we consider this Hecke algebra action on this stable basis. So SI is a simple reflection, and if WSI is bigger than W under the Broussard order, so then the action of this simple generator TSI in the Alban-Hecke algebra on the stable basis is just very simple. Just the right multiplied by this SI, and this we have this Q to the 1/2 because of these normalization conditions for this stable basis. We can make this to be 1 by choosing appropriate normalizations. Okay, so this is almost the same as before. But so although here I only write the case WSI is bigger than W, but so how about this when WSI is smaller than W? So then this you can use the usual trick about this Hecke algebra. So you can always use this quadratic relation to get the formula when the WSI is smaller than W. Anyway. So this says this so this basis will form a standard basis for the action of this finite Hecke algebra. So the stable basis should always behave as the standard basis. Okay. So this is only for this positive chamber and also for this member L, i.e. for okay. So maybe let me just mention. So this L will depends on locally constantly on this on here. So finally, so this L will only depend on the choice of this L curve inside here, inside here, and then and here we are picking the fundamental L curve. So okay, so and in another collaboration work with Gufang Zhao and Zhong. So we studied this stable basis for arbitrary chamber and arbitrary L curve W's. So that is to say we can determine all the stable bases. So the result roughly says as follows. Okay, so it's so the other well chambers they are indexed by the well group, so they're related by the well group. So if you go from this dominant well chamber to another well chamber, let's say so if you go from the positive wire chamber to another wire chamber, W applied to that. So then so the stable envelopes. So then this is just the wire group action, the W action. So what does this mean? What is this wire group action? Because everything lies in the KCL class on the coordinate bound of the flag variety. And on the coordinate bound of the flag variety, we have the coordinate bundle of the coordinate bundle of the flag variety have a G action, and then this will induce a wire group action on the equivalent case ring. Yeah. So then this is this wire group action. Okay. So this is the change. Yeah, this is the change of these chambers, and the change of these alcoves is again let me not write down. So then the change of alcove will be given by these hack operators. So anyway, okay. So once we have this, so then we can determine all these stable bases for arbitrary chamber and for arbitrary alcoves. So then we can categorify this using this affine brief group actions on the derived category of coherentials on the spring resolution constructed by Simon Rich and Roman Okounkov. Anyway, so let me, okay, so then this is about the hack algebra action. So, and also similarly, in the, we can see this hack algebra action on the zero section level. So we are going to introduce a generalization of this Chen-Schwarz-McPherson classes called the case-theoretical generalization. And this is called this multiplic Chen classes. So again, so this will be a natural transformation between two functors. And the first functor is as follows. The first functor is the functor of this Grothendieck group of varieties over some variety. So Y is the algebraic variety over the complex numbers. Then we can form this the relative Grothendieck group of varieties over Y. By definition, this is just the isomorphism classes of the varieties Z mapping to Y, and we model out this relation. So U is some open subvariety inside Z. And the other functor is just the K-series functor. So this generalization is due to Brasilet, Schürmann, and Recurrent. So their theorem says the follows. So we have this Grothendieck group of the relative varieties of functors, and we have this K-series functor. So then their theorem says there exists a natural transformation denoted by MCY. So here, so Y is a formal variable. So in the target, we are drawing this formal variable Y, such that it satisfies the following normalization conditions. So if we start with the smooth variety Y, and then you can consider the identity map Y mapping to itself. So this will lives here. Okay. And so then the image of this identity map will gives you this. So this is called the K-theoretical Euler class, denoted by lambda Y of coordinate bundle of Y, i.e. So the summation over I, Y to the power of I, and then this Y to the power I of the coordinate bundle of this smooth variety. Okay. So the natural transformation just means so then this will commute with proper push forwards. Okay. So this is so then this is the case-theoretical generalization of these CSM classes. Okay, so then let's restrict to the flag variety case. So we can see the Schubert cell embed into this flag variety, and then we apply this natural transformation. So then this will give you some K-series class on the flag variety are doing some form of variable y. I forget to mention. So their construction is in the non-equivalent case, and this can be extended to the equivalent case. So the Torah equivalent case theory. Okay, so as before, let me just use MCY of XW circle to denote this K-theory class. So again, so then this will have the action of this F1 hack algebra by convolution by using this result of Kastan-Lussiger and Ginsburg. And this action is computed here. So if we start with some simple reflection, and if WSI is again bigger than W under the Bull-Head order, then the action is this TSR action just changes one Schubert cell to the other Schubert cell. So again, so this is the case when WSI is bigger than W. We can use the projective relation to get the action, to get the formula when WSI is smaller than W. Okay. So then there are several consequences of this theorem and the previous hack algebra formulas. So first of all, so the stable basis lives inside the coordinate bundle, and then again we can just pull back this to the zero sections, to the flag variety. So then this will coincide with this multiplicative chain classes of these Schubert cells. So the precise formulas will be up to canceling by some factors. Yeah, but those factors will be the same. Those factors will not depend on this W. So anyway, and so in another work with Aluffi, Mihalcea, and Schürmann, so we give another construction of this multiplicative chain classes using this mixed Hodge modules on the flag variety. Using the mixed Hodge modules on the smooth varieties, i.e., so we can consider the Grothendieck. So anyway, so let me just talk about the flag variety case. So we can consider the Grothendieck group of this Brier equivalent mixed Hodge module on the flag varieties. So then, okay, so this is some black box. So this element here will consist of a holonomic D module and also a post shape. They will match with each other on the Riemann-Hilbert correspondences, and also there is some nice filtration on this D module called the Hodge filtration, and also there's another filtration called the weight filtration, and satisfying some nice properties. So that okay, let us just remember this good filtration on the D module, and then we can take the associated gradient with respect to that good filtration. So so then we will get some Tolkien shift on the coordinate bundle of the flag variety. And we have, and also this will be C star equivalent. So recall this is C star only acts on the coordinate fiber. So then this is C star action. So then this C star equivalence comes from this comes by taking this social gradient of a Hodge module. Anyway, and now if you so if you combine so then this just says the stable basis elements will be just the associated gradient of some constant mixed Hodge modules of a Schubert cell. And this is so this result is really so it's really analog of this result. I should also say, so then this is also the same as characteristic cycle of this constructor function on the Schubert cell. Yeah, so these two are equal to each other. So this is well known in the Kastan-Lussiger theory. Yeah, and yeah, so then so similar results is claimed in the book of Andre and Davish. So then, i.e., they claim this is true for all the coordinate bundle of the for all the coordinate bundles. And anyway, and then in the K-theory case, well, yeah. So in the K-theory case, we say the K-theoretical stable basis is also equal to some characteristic cycle of some mixed modules. So I don't know whether this will hold in the general situation for the general coordinate bundle or not. Anyway, so this is about this hack algebra action and the deformation of these usual Schubert classes. And then, so this is the hack algebra on one side, and then we will see the hack algebra on the dual side. So the case theoretical case is more interesting because this our hack algebra has another interpretation. So the hack algebra on the long-length dual side. So here, let us consider some non-Archimedean local field F. So you can just consider this consider a finite extension of the p-adic numbers, or you may consider the finite extension of this formal Laurent series. So fp or join this t. Anyway, and we use k of f to denote the residue field of the ring of the integers. So this will be a finite field, and let's say this is fq. So this q is the same as before in the hack algebra. Oh, I forget to mention. So this formal variable y just equals this negative q. Yeah. So yeah. So here, so this is negative q. So here in the non-equivalent case in this theorem, their construction involves a formal parameter. I don't think they have a good explanation for this formal parameter formal parameter. But in this construction, that formal parameter y is just corresponding to this equivalent parameter for this C star action on the coordinate fiber. Okay. So y always equals negative q in my slides. So then we can consider this G check, which is the dual group over this non-Archimedean field F, and we can also consider the dual groups, dual torus and the dual Borel subgroups, and the I is the Iwahori subgroup. So IE. So you can consider the all F points of G check, and then sorry. And then you can model out the maximum ideal, then you get to the KF points. And then here we have this Borel subgroup. And then the inverse image is this Iwahori subgroup. And then you can consider this competitor supported functions on the F points of the dual group. And we also require it is left and right invariant under this Iwahori subgroup. So then this will has a algebra structure by convolution. So if you have two functions, because it's left and right invariant on the I, then you can consider their convolution. So then this has an algebra structure, and this is called the Iwahori hack algebra. And it turns out, so this algebra is isomorphic to our previous hack algebra, isomorphic to this Alban hack algebra. Anyway, so then this is the analog of this equivalent case of the equivalent case of the Sternberg variety on the dual side. But our stable basis lives on the equivalent case of the coordinate of the flag varieties, not the Sternberg variety. So then what are the analogs of the case theory of the coordinate bundle of the flag varieties? So then this is called the principal series. So if you consider a character of this dual torus, and we impose further conditions. Anyway, we impose further conditions such as this tau will correspond to an element in the original torus. Anyway, so we can just consider the inducible representation, and then we form this. And then we consider the invariance under this Iwahori subgroup, the right invariance under the Iwahori subgroup, and then we denote this by I of tau. So then this space, you can just think of this the functions on the dual group, which will be right invariant under the Iwahori subgroup. And then because you use the right invariance and also use the left invariance in the hack algebra here, so then we can then this algebra will act on this I of tau by convolution. Okay. So then this will be our analog of this K series of the spring resolution. So and then there are natural bases inside this invariance. So one is just this denoted by phi of W. So this phi of W just you can just think of this as the identity functions on some cell on inside this group G. And the other basis is FW. Let me know. So this is introduced by Schürmann. Let me not write down the definition. So anyway, so the next properties of this basis is follows. So then, so recall this so this Alfvén-Hecke algebra. So the Alfvén-Hecke algebra has two parts. One is given by this finite Hecke algebra, and the other part is given by this lattice part, i.e., the equivalent case of a point. Right? So then, so the next properties of this is the following. So then this is eigenbasis. Eigenbasis for the lattice part inside this Hecke algebra. Okay, and then so once we know this, so then it will be very easy to identify this with the basis on the original set. Okay. Yeah. So then the theorem says follows. So we have this this evaporating invariance I of tau, which is a Hecke algebra module, and on the dual side we have this equivalent case of the cotangent bundle of the flag varieties, which is also a Alfvén-Hecke algebra module. But the right hand side depends on tau. So and on the left hand side tau so recall tau is an element in the dual torus. So then the equivalent case of a point we has a this will has a natural representation. Just the evaluation at this tau, right? Because this is the Laurent polynomials on this torus, and now once you have a point, then you can just evaluate at that point. You get this one-dimensional representation. Okay, so then it says there is this unique Hecke algebra isomorphism such that this WB just denotes the fixed point, the torus fixed point corresponding to W, and this just denotes the structure shape of this fixed point. So then this is the fixed. So as W runs over the Y group elements, so then this is just the fixed point basis, and then this will correspond to this Schürmann basis, and this stable basis will correspond to this standard basis to this characteristic functions of some cell. Yeah, recall previously. So then this stable basis also corresponding to some characteristic of some function of some cell. So it's really of the very similar shapes. Okay, so this so it's very easy to see that on the localized equivalent K series. So what are the eigenbases for the I forget to say. So the lattice part inside this Alfvén-Hecke algebra, how does this lattice part acting on the equivalent case of the cotangent bundle of the flag varieties? So this lattice part is i.e. x lambda is a character. So the action x lambda on here is just given by the tensor product with this lamb bundle L lambda, and then what is the eigenbasis for tensoring with the lamb bundle? That is the fixed point basis. So so this is well expected. So anyway, so once we have these two identifications, so then we can. So the first result is so on this dual set there are many classical formulas called this McDonald's formula for these spherical functions, and also this Schürmann-Schaliker formulas for these spherical Witta functions. So anyway, so once we have this identification, we can get a case theoretical interpretations of these formulas. Anyway, and then we can also reprove this just using localization very easily. So another application is as follows. So then on this dual side, we have these two bases. So then people are interested inside this transition matrix between these two bases. And then we can use this to prove. So that Bang and Naksuji and Narusi, they have some conjectures about this transition matrix coefficients, and we can prove this just using this theorem and also using another result I'm going to mention later. But first of all, let me mention. So first, so the transition matrix here will correspond to the transition matrix on this K-series set. And this set, the transition matrix between this fixed point base and stable basis. So then Dutch matrix is just given by the localization of this stable basis. Okay. So that's so we get anyway we get a geometric interpretation for this matrix coefficient. And another okay, so yeah, so what is their conjecture? So let me not write. I'm not going to write down their conjecture, but I'm going to write down the corresponding geometric statement. So the statement is so the geometrically says the following. So this is called a smoothness criterion for the for Schubert variety. So we consider this Schubert variety XW, and we consider another torus fixed point. So we consider another element in the Y group. U is smaller or equal than W. So then this is another torus fixed point, and because U is smaller or equal than W, then this torus fixed point lies inside this Schubert variety. And then our result says follows. So the Schubert variety is smooth at this torus fixed point if and only if the localization of this case of this multiplicative chain classes, which is some case theoretical classes, at U is given by this formula. So then this lies inside K0 of a point, drawing this Y to the power plus or minus 1. So anyway, we get some smoothness criterions for the Schubert varieties using the localization of this multiplicative chain class, or in another way around, or using the localization of this stable basis. Okay, so first of all, so they so in literature there is a very odd result due to Kuma, which is also a smoothness criterion for the Schubert varieties. So Kuma's theorem says as follows. So the Schubert variety is smooth at this fixed point if so this formula is happening in the equivalent cohomology of the flag variety. So we consider the fundamental class of this Schubert variety, which is some cohomology class, and then we pull back to this torus fixed points. So then this has to be this form. So so this one. Yeah, and so this is written in terms of the equivalent cohomology, and then so this is our result is in terms of this equivalent K theory. One direction is very easy. So once we have this, so then we can just spatialize Y to 0. I forget to mention. So if we spatialize Y to 0, so then this class is just becomes the ideal shapes of this ideal shape of the boundary of the Schubert divisors. And so if you let Y equal to 0, so then this will vanish. But again, we are in the K series side. But if you use the chain character map, we can go to the cohomology, and then we can get very easily to this formula. That is one direction, and the other direction. So the other direction we'll use is the functorial properties for these MC classes. It depends crucially on this commutes with these proper followers. Anyway, So this is our generalization of Kummer's result. And why is this useful then? So Kummer's result is even simpler, right? So this is useful because because this recall these classes are generated by the Alfan-Hacker operators, and for the torus fixed points, so then this is also generated by the this will be generated by the while group actions, and then this just says we can write everything in terms of algebra just using the constant Kummer-Hacker algebra. Anyway, yeah, so we can write everything in terms of this constant Kummer-Hacker algebra. So inside this Hacker algebra, we have this while group actions, and then we can also form these Alfan-Hacker operators. And then, this result, can be translated into the following. So we consider the corresponding Hacker operators, and then we expand into the while group operators, and then the transition matrix will have to be like this. Anyway, so we have a purely algebra statement for this, and so we use this to prove some conjectures of this my collaborators, Christian Lenart and Zainoulline and Zhong. So what they conjecture is the following. So they studied this hyperbolic cohomology of the flag varieties associated to this form of group law. So then it is well known in Schubert calculus that in this cohomology, so then the class of the Schubert then the Schubert class is not well defined. It will because if you take the Bode-Sampson resolution and then you want to define the Schubert classes, so then this will depend on the choice of the reduced word. So their goal is to define some Schubert classes which does not depend on this reduced expression, and then they call this custom-Lucid Schubert classes. So the rough idea is the following. So inside this hyperbolic cohomology of the flag varieties, we also have this this Hacker algebra action, and then so inside this constant Kummer-Hacker algebra, then we can form this Alfan-Hacker operator, and then furthermore we can form this from the canonical basis, i.e. the custom-Lucid basis inside this Alfan-Hacker algebra, and then so my collaborators, they use this canonical basis, custom-Lucid basis to define to generate some classes, and they claim that these classes will coincide with the usual Schubert classes under some good conditions. Anyway, you can just use this reformulation to prove that. Okay, so then this is about the Hacker algebra action and the smoothness criterion and the comparison with the long-line dual set. So any questions? Okay, so finally, so another good properties of this multiplic chain class is as follows. So if you have some character lambda of the maximum torus, so then we can form this line bundle on the flag variety. So then you can consider the equivalent Euler characteristic of this line bundle L lambda. So by definition, this is just the alternating sum of the cohomology of this line bundle. So then this lies in the this lies in the equivalent case of a point. So this will be some Laurent polynomial, and so this is well known, right? So then this is just given by the usual well character formula. So I think Andre almost asked his students during their oral exams this question. So anyway, and also there is a slight generalization of this formula due to the Mazur, i.e. So we can define some operator partial I called this the Mazur operators. So partial I apply to in lambda. anyway, so just define it this way. So then if you replace this L lambda by this by this tensor product, L lambda tensor with the structure shape of a Schubert varieties. So then this is just given by the partial W applied to E lambda. So then this is called this Demerzel character formulas. Okay, so this partial I will satisfy the Braid relations. So then in particular, with the partial W is well defined. Okay, so then in literature there is also a generalization of this Demerzel character, Demerzel operators, i.e. called Demerzel-Lussick operators. Okay, so Y is always negative Q. So anyway, so defined in this way. So if anyway, so formula is given here. So we can, by taking special values of this Y, we can reduce to this Demerzel operators. So then the result is the following. So if you consider this line bundle L, but we tensor with this multiplic chain classes, but now we have to divide by this K-theoretical Euler class of this cotangent bundle of X. Okay, so now so my collaborators, they called so we call this class called the secret classes. So now if you consider this equivalent Euler characteristics, and then we times these factors, so then this just give TW applied to E lambda. So again, so this TSI will satisfy the Braid relations, and then this TW is well defined. And then this is exactly this your Horowitz functions on this dual set. So recall we have on the dual side we have this if you remember, so we have this the characteristic functions of a cell, and then so using this we can define some Witten functions, and then so these are equal to each other anyway, and let me not write down the definition. So this is for only. So this is only for one characteristic functions, and then if you add them together, so if you sum over all the w's, so then we will get this Kessler and the Shalika formula. Yeah. So this is all I want to talk about. I'm sorry I finished earlier again. Yeah. Any questions?
Yeah, we have thanks, Changjian. We have 15 minutes for questions.
Yeah.
So, how about questions?
Yeah, if we have extra time, maybe can you explain how to think about this motivic churn class? Or just maybe for some basic examples other than the identity map?
Oh, that other than identity map, how then if you upstream map, I don't know. So we only consider this inclusion maps. Okay. That should be okay for you? Sure.
Yeah. Anything you can see.
Yeah. So thanks for asking. Yeah, I should prepare some examples for this chain class series. Yeah. So the basic ones is again, so the P1 case. So if you consider this so the embedding of this point, so then this is so then this is really just the structure shape of that point. Okay, that is easy. And then if we want to compute the inclusion of this other Schubert cell, so then here we need to use this this relation in the Grothendieck group. So then you can just use the. But I think you may not be satisfied because again this is an identity map, and then minus n y of. Yeah, and then this is the definition here. Yeah, this is the the simplest example I can write it down now. Yeah. So usually we just break we will use the relations in the Gaussian group to make this into a proper map, and then we can use the functorial property to just concentrate on the source, and then we use some and then we use the normalization conditions to compute this. Is that okay, Noah?
Yeah. So,
but in principle, you can compute it by like resolution of singularities, right? You have some map, you can resolve the singularities.
That's
and
right.
right.
That is right. Yeah, that is how they prove the existence. Yeah.
in
So maybe what Zhang says that of course the identity map uniquely determines what this is, but if you have a smooth map, that's also you can just write down what the answer is. I think it's and then the general map you resolve. That's the strategy. I think.
Exactly. Yes.
And
Mm-hmm.
can you can I get, say, the K-theoretic classes you were thinking about, or the cohomology classes you were thinking about from this? Like, does this decategorify in some sense to those invariants, or is this something kind of orthogonal to?
Can you repeat your question? I didn't quite understand.
Yeah, I guess how does this relate to the kinds of classes you were thinking about in the first part of the talk, in the part on cohomology?
Oh, the cohomology case. I don't know a good relation, but I think this is I don't know actually. Yeah. Maybe Andre had a better answer. Yeah, I don't know how to relate the K-theoretical stable angles to the cohomology one actually. But on the flag varieties level, there is such a relation, but also not very. Due to my collaborators. So in their paper, they do have some procedure to go from K theory to the cohomology case, such that this will really specialize to the chain Schwarz McPherson classes, but that is not very direct at all. Not just taking the chain class, taking the chain character directly. Yeah. Andre, do we have a better answer?
I don't know. I need to think about this. I'm not sure. I think they're both instances of elliptic stable envelope, but kind of different instances slightly. So I'm not sure how to exactly relate one to another. Speaking of that, I had a question at the points. Remember, there was a point when you spoke about like if you take different both samples and resolution, that will give you different answers.
Yeah,
it was this part, and there's of course a very parallel story elliptic cohomology, and that what people realize there that you should dissociate. So of course, in elliptic cohomology, we're not asking for elliptic cohomology. It's not like it's not some kind of algebra. It's more sections of some line bundle, some variety, and so you should ask not for some one element, but rather for a section of some line bundle. That line bundle has some moduli, right? So you get instead of getting expression in the variables that you want, you get expression in the variables that you want plus some auxiliary variable. And that what happens in elliptic cohomology is by memory from the talk we had like a year ago. Is that if you want that variable removed, you want to set that variable to 1, then okay, there's going to be a poll, and depending, what you do with that poll, you're going to get all different both samples and resolutions. So is there do you think there's might be some effect like this in this story, or it's just something else?
I don't think so.
So there is no way to add some variables that. So the reason I'm asking is that in the general theory of quantum groups, of course, once you go to elliptic quantum groups, then the dynamical parameter is unavoidable. Elliptic quantum groups, they're always dynamical. But in principle, there are like dynamical R matrices for, ordinary, like, trigonometric dynamical R matrices. And so in principle, I mean, there exist. Such things have been studied. And maybe you can have some kind of dynamical variable somewhere in the story, so that is that conceivable?
Not to me right now, but I think the talk you mentioned is Richard's talk, right?
Richard's talk. Yeah, Richard's Riemanni's talk. Yeah, exactly. Yeah.
Yeah, they can do it. Yes, that's true. In the elliptic case, yeah.
Sorry, this reminded me of that question that he was answering, and that his answer included an extra variable. And I was wondering if maybe there's some extra variable hidden in what you're talking about. I mean, you can be added to what you're talking about to get kind of that kind of dynamical Hecke algebra. Is there must be such an object like dynamical Hecke algebra?
Okay. Okay, I don't know.
Okay, all right, sorry. I guess that wasn't a well-defined question. Well, I guess if there is a dynamical Hecke algebra, that is a question, right? So one can be answered, or yes or no. So, but maybe not right now.
Yeah. Oh yeah, I forgot to mention. So many parts of this story in Taipei is also a result of or results of Richard Riemann, Wachenko, and Tarasov and their collaborators. Yeah.
All right, more questions?
At some point, you have like a stable basis and McDonald basis, right?
McDonald basis? No.
No, on this. Like
no.
when you talk about transition, no, not maybe exactly. Yes, here has.
Yeah.
Like,
yeah. So this is only about the McDonald's. This is spherical functions, not the McDonald basis.
Yeah. Sorry.
No problem.
Do you understand correctly that you know about this transition only when Schubert variety is smooth?
No. We know this in general. But when the Schubert variety is smooth, then this formula has a factorization. Yeah.
But you have a formula in general, okay?
Yeah, but that's a very complicated formula. Yeah. Yeah.
Okay, and also maybe I was a bit lost at this point of your talk. Is it finite characteristics setting?
Oh, that is a very good question. That is right. I didn't mention where is it? Yeah. So I didn't continue here. So as I said, we can determine all the stable bases for any chamber and for any non-bounded L, and then you can use this affine break group action due to Simon Rich and Roman Bezitankov to categorize this. You can get objects in the derived category of the coherent shapes on the spring resolutions over the integers, and then you can go to the finite fields. You can and then we use these results of Roman and Mikovic and Romania again. So they are localization equivalents, and then those categorified stable bases will coincide with these Roman modules over positive characteristics. Yes.
Maybe I should add that Macdonald's spherical function is the value of Macdonald polynomials at c equals 0, right?
That's right. Yeah.
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 More questions? Well, then if not, then maybe we should all thank Changjian again for a wonderful talk, and we'll see each other next week, same time, same place. So thanks everybody.
Thanks for listening. Yeah, every time I give a talk at this seminar, I will usually end earlier.
Everybody's happy when the talk ends early, I think. All right.
Okay.
To be continued next week.
Bye, everybody.